In this video, we're going to look at calculating amounts or quantities of energy transfers in and out of a system or within from one object to another. The measurement of that energy transfer, and again, we're only talking about the first part of energy that we're going to deal with, which is thermal energy or energy of moving particles. Next comes up, what we do after this is we'll look at energy changes that are potential energy. But for right now, we're on to thermal energy, which is the kinetic energy of particles. So we said in the last video, if I'm going to take cold water and make it become hot water, and it goes for more than water, but any substance, and get it moving faster, I'm going to have to put energy in to do that, right? So to get it from here to here, energy in. And here we're going to start to calculate how much energy is that going to take. It depends on a few things. And of course, energy is completely reversible. I put a certain amount of energy to get this from cold to hot. To reverse that process, take that hot water and turn it right back into the same temperature cold, then what's that going to do? If I go in the reverse, the exact same amount of energy is out, right? So energy is reversible. Certain amount of energy to heat it up. If I cool it down by the same amount, I get that same amount of energy out. Now, most of our energy transfers that we're going to look at are going to be in terms of heat. And so we're going to be taking, maybe it's water, maybe it's a block of metal or some sort of solid, and I'm going to apply heat, transfer heat energy in or transfer heat energy out. There is other ways, other types of energy transfer. The sun, right? Nice happy face sun. If I put a beaker of water out in the sun, there will be energy transfers into here. That would be radiant energy and not heat energy. So we'll look at that less. Really, we're going to talk about heat energy. Okay. I'll leave our happy sun up there. It's summertime. Okay. Now, as we know from before, let's say I've got some H2O. It's at 28 degrees C. And I put in some sort of block of hot metal, and it's at 90 degrees C. And I drop that in. What happens, since this is hotter than the water, then the metal is going to give off energy to the water. Heat is going to flow, or a transfer of thermal energy from the metal to the water. For how long will that go? Until they reach the same temperature. When they're at the same temperature, we call that thermal equilibrium, right? When they reach the same temperature, then there's still some movement of particles and collisions of particles, but the energy flow in and out of the metal is the same. Now, the total amount of energy that transfers depends partially, yes, on this difference in temperature, but even if energy goes from hot to cold, even if I take just a little speck of metal, that's at 90 and the water is 20. So it doesn't matter how much you have, how much materials you have, energy flows from hot to cold. Now, of course, part of it depends on how much stuff I have, but there's something else that's a factor here. Let's say I have 1.0 gram, a small amount, 1 gram, and it's H2O, and it's at, I'm going to pick a temperature, 25 degrees C. I want to heat that up. I'm going to speed up those water molecules. I have 1.0 gram of H2O, and it's now, I'm only going to heat it up a little bit. I'm going to raise it from 25 to 26. So I'm speeding the particles up. I'm going from here to here. To do that, speeding them up, take some energy in. I'll put a big arrow. I got to put some energy, not very much because I've got a very small amount of water, and I'm only raising 1 degree. But that's been calculated, right? This is a property of water, and only if it's water. So importantly, I'm saying, what material am I talking about? It's water. And so it takes 4.18 capital J joules. So joules is a unit for energy, and really it's the only unit we're going to use in this class, right? So joules. Yes, there's calories, there's different kinds of energy stuff, energy units, but all we're going to use is joules or kilojoules. So this is a property of water. How much energy does it take to heat water? Because all substances are different, as we'll see. So 4.18 joules, that's a property of water, just like water has a certain density, that's a property of water. And so this is a property of water. It's called the specific heat, right? It takes a specific amount of heat energy to take 1 gram of water and raise it by 1 degree. Now this I just picked a starting point, but the key is the change. How much am I going to change the temperature? So the specific heat of water is that it takes 4.18 joules of energy to take 1 gram of water and heat it 1 degree C. So it would be 4.18 joules per gram degree C, right? Joules per gram per degree C. That's called the specific heat. Water has a pretty high specific heat, which means it takes a lot of energy to change it. Remember also, before I erase this, if I were to reverse this and instead of heating water, I'm going to cool it by the same amount. I'm going to take 26 degree water, turn it to 25. I'm going to go this way. How much heat? In this case, it's losing energy. How much energy does it lose? Same amount, 4.18 joules. So this is reversible. It goes to heating and it goes to cooling. If it's not water, so this is the specific heat of water. Let's say it's a copper metal. I got the same amount, 1.0 gram copper, and it's at 25 degrees C. I'm going to heat it up so that I've got 1.0 gram copper, 26 degrees C, same amount. But it's no longer water, now it's copper. Copper and metals are usually a lot easier. They change temperature with a lot less energy involved. Let's see, copper. There's different alloys of copper, but on average, 0.385 joules to do that. So the specific heat of copper is 0.385 joules per gram per degree C. That's the amount of heat it takes to take 1 gram of copper and heat it by 1 degree C. So you can see water is more than 10 times this. It takes more than 10 times the amount of energy to change the temperature of water than it does just something like copper. So that's just one of the properties of materials, like density, like other things. And it's called the specific heat. And that matters, right? So let's go back to our little water piece. And so this amount, water, 4.18 joules. Well, okay, so that tells us for water how much to heat 1 gram. What if I have 10 times that amount? Instead of 1 gram, I've got 10 times the number of molecules, 25 degrees C, and without me drawing all of that. If I have 10 times the amount, I'm trying to speed up the same amount, but I got 10 times as much to do it. It's going to take 10 times the energy. So that would take, instead of 4.18 joules, that means 41.8 joules. So far we found two things. How much energy does it take to speed up water molecules? It depends. It depends on, well, for one, it's water, right? So it's based on the property of water. And then it depends on how much water I have, and let's go back to our 1 gram of water. I'm just choosing 25 degrees C. This would go for, you know, any temperature. But now my change, I want to heat it up more, not just 1 degree. Let's go 10 times the temperature change. So we're really interested in temperature changes. The same would go for if I was going from, say, 10 degrees to 20 degrees. A 10-degree temperature change, instead of just 1, my change in temperature, or the amount of change of their average energy, is going to be 10 times as much. How much would it take? Instead of 4.18, 10 times. So what we have is the relationship, and this is our calorimetry equation. The heat energy transferred. Because this applies for transferring it in or transferring it out of a system. Depends on 3 things. The mass, how much stuff am I trying to heat up? The specific heat, and I'm going to have to erase my happy sun, the change in temp. So the energy required or transferred in if I'm heating or transferred out if I'm cooling, it depends on these 3 things. How much am I trying to heat up or cool off? What is the substance? What is the property of this substance that I'm trying to change the temperature on? And how much am I going to change its temperature by? In equation form, Q for heat. I know why shouldn't heat be H, but it's Q. I don't know who decided that. M for mass. Specific heat gets a lowercase c. Change of temp is delta T. Delta stands for change, right? So we're not talking about absolute temperature here. We're talking about the change in temperature. When I look at specific heat, wow, joules per gram degree C. But since the change from degree C to Kelvin is just a shift in the 0 point, a change of 1 degree C is also a change of 1 Kelvin. So sometimes you'll see the units written joule per gram Kelvin, right? If I'm going from 0 to 1 degree C, if I'm changing 1 degree C from 0 to 1, I'm going 273 Kelvin to 274 Kelvin, right? So a change of 1 degree, if I'm talking about change in temperature, a change of 1 degree C is equal to a change of 1 degree Kelvin. Okay, so we can look at that in certain problems. And let me just work one sample problem and set up another. So let's say I've got 45 grams of water. And my water is at 22 degrees C. And I'm going to increase it to 75 degrees C. So I'm going to change its temperature from 22 to 275. Let's go with, let's just plug that into the equation. So I'm going to put it in up here. The energy needed, my mass of water is 45 grams. And I did specify that it's water, right? Because if it's not water, it's going to be something different. For water, it takes 4.18 joules per gram degree C to heat that water up, to change the temp or cool it down. My change in temperature, we would usually write T final minus T initial, based on where my starting point. So subtract my starting point from my initial. Now I've calculated all that out, and I got 9,900 and 69.3. Okay, too many sig figs. That's J for joules. Round that off to 2. So let's see, 1, 2. I got to round up 10,000 joules. 10,000 joules means, let's see, wait, I want to show 2 sig figs. I got a problem. Let's change that to scientific. 1, 2, 3, 4. 1.0 times 10 to the 4th joules. So that is the amount of energy that it would take to heat that water up. So 1.0 times 10 to the 4th joules. The other thing we could do, now I mentioned earlier that joules is our unit for energy. We can also use kilojoules. So 1,000 joules equals 1 kilojoule. So joules are kilojoules because joule is a small, that's not that much water, and I'm not doing a big temperature change. Joules is a rather small unit of energy. So sometimes we'll refer to kilojoules. 1,000 joules is a kilojoule. So if I have 10,000 joules, I have 10 kilojoules, and I can show a decimal point there just to make my 2 sig figs. Okay, so that's how we're going to calculate. I'm going to add some more complicated problems a little later. What happens if I take a hot object into a cool object, and we'll set that up. But let's practice some calorimetry and then continue on to potential energy.